We're live.
And I will welcome everybody to the nth Triumphs webinar, where n is one more than the number that we have had before today. And thank you for joining us. For people who have not participated before or who are seeing this video on our website, I would let you know that Triumphs is an NSF-funded project that is designing, using testing projects to teach standard topics in undergraduate mathematics from primary historical sources. There's a lot about the project on the website, including about the research component of it, and I encourage you to take a look if you have time and interest. The website has been pulled up on the screen here and shared by Danny. Address is up top, but if you Google simply Triumph's primary sources, we will be the first hit in your favorite search engine. We want to give people who might want to use our project a chance to learn about them and hear about them from the person who designed them, to talk about how they could be used and what you could expect in the classroom. And I'm pleased today that Danny Otero will be talking about one of his new projects, or maybe more accurately, two very closely related projects on completing the square. Danny will share now. You are welcome to interrupt him if you have questions, but whether you do or not, when we're all done, we'll have a time for question and answer. Last thing I would say for those of you who are joining us for one of the first times, please note in the lower left of your Zoom window is a mute button. During the presentation, you may want to mute, just so if there's any small noises on your end, they don't get shared with everybody. Turn it off, of course, anytime should you want to ask a question. Take it away, Danny.
Okay, thank you, Dominic. Dominic, you want to introduce yourself, just in case people don't recognize your face?
That's always good practice, isn't it? I'm so sorry. Hi, I'm Dominic Clevey. I'm one of the principal investigators for the Triumphs Project. I've been working with the other 6 people for the last 5 years now. And I'm also here if you have any questions.
Yeah, you can see our names. The PIs are listed down here on the bottom of the front page of the Triumphs website. While I've got the website up, I can also let people know that there is a appeal going out to people who are interested in using Triumph's projects in their classrooms, and also willing to share data from you and your students about implementing one of these projects. That information is down here. Dominic, you want to say another word or two about this?
Yeah, that would be great. Anyone's welcome to use our projects anytime, but we really love when people sign up as official site testers. It involves some instructional survey from you, possibly some surveys of your students. And if you're willing to do this for us, it would be great, because we would get a lot of feedback at how the project is used and whether or not it should be changed in some way. We can also pay you for this. So if you apply and are chosen, you'll get a stipend of between $200 and $500 for our thank you for your efforts in helping with this data collection. If you look at the website there, it says that you should apply before October 15th. We've decided to delay that until the end of the week. So you have until this Friday. But if you haven't done so, please do take a look at the projects. We would love to have you give this a try.
Great. Okay, again, before I leave the website, there are these important menus at the top. You'll see here on the right where this webinar is going to get posted in recording, and where a couple of our other webinars, most of the webinars that we've run are available here in recording. Also, the first of the menus gives you a list of all of the Triumphs projects. In particular, here are the ones that are available. Not all the ones that have been planned are ready yet, but here are the ones that are available. And they're also organized by discipline. The ones I'm going to talk about today are down here in the pre-calculus and trig section. I'll also mention that, as Dominic indicated, I'm actually talking about two projects today, one of which is a longer, week-long or so project. The other, we call it a mini because it's 2 days or less in planned classroom use. That is an edited version of the longer one. Here, I think I'll take that opportunity to stop sharing that website. And I'm going to bring up a copy of the other one. So just a second. There we go. So what you have here on screen is a PDF of the shorter of the two projects. This is one that I'm going to spend the next 15 minutes or so talking about. I'll allude to the longer one in a bit. I'll also mention that this is the latest version. I think the one that's available at the Triumph's website is an earlier draft of this. If you're really interested in using this in a classroom sometime soon, I'm sure this version will make its way onto the website in a couple of days. But if you really want to take a look at it quickly, I invite you to contact me by email. Let's see. In fact, there's my email at the bottom of the front page here. So I invite you to contact me and I'll send you a copy. In fact, that also goes for the longer one. The longer one, it's a somewhat complicated story, but the mini got a write-up in Convergence recently, and I took that opportunity to revise the longer version of the project. So that also has a more recent date attached to a better updated version. All of this will eventually make its way onto the website, hopefully by the end of the week. But again, if you want to get a copy for yourself, do contact me. All right, so what's the point of this project? This project was designed to serve a couple of populations. First, and probably most obviously, students learning algebra, in particular, learning to solve quadratic equations. It's a standard rite of passage in virtually every student's mathematical education. It's clear to me from the times that I've tried to help students with this that quadratic equations leave students with this belief that mathematics is manipulations that have some sort of indecipherable magic behind them. And I'm trying to, in this project, through the words of Al-Khwarizmi himself, show you that this is just problem solving with some clever ideas thrown in, and there's nothing impenetrable about it. In any case, I talk here in the introduction to students and instructors about how I understand the introduction to solving quadratic equations can sometimes be challenging for students. We typically teach them how to factor quadratic polynomials. The goal is to try to do problem solving, be able to solve quadratic equations. Clearly, not all polynomials are factorable, so not all quadratic equations can be solved unless you learn other methods. The standard one is completing the square. It's typically handled as an algebraic method, even though completing the square is obviously related to some geometric process. That's rarely shared with the students. That's one of the main goals of this project, to show the student that completing the square makes perfect sense if you think of it as completing a square. And then that's translated into symbols. In fact, one of the nice benefits of the project, I think, is showing students early on that algebra itself has as its origin problem solving that isn't necessarily symbolic. In fact, let me move right into the meat of the project to show you. This section 2 tries to put some context here. I give a short historical introduction to Al-Khwarizmi and the compendious book on calculation, today called simply the Algebra, in which Al-Khwarizmi solves a host of problems, including quadratic equations, or problems that today we resolve as quadratic equations. And he does so entirely rhetorically, right? By which I mean there are no symbols in Al-Khwarizmi's algebra. And so I think it's useful to let students see what Al-Khwarizmi does, because indeed we point to him as the quote unquote father of algebra, and yet he uses no symbols to do his problem solving. This is where I begin to orient students to Al-Khwarizmi's language. And the way he formulates his problems, like squares are equal to roots, roots are equal to numbers. These are familiar equations that students by this time in their education have solved, but clearly not in this rhetorical form. I have students think about this in the first couple of tasks, asking them to translate Al-Khwarizmi's language into modern symbols, and see how what Al-Khwarizmi doing here is connecting to the sorts of things they find in their textbooks. In particular, in this task 2, I really want them to think about the context here. So I ask them to reflect on what they think Al-Khwarizmi means when he says that what he's doing is providing what people generally want in calculating. That should make for interesting discussions, both in the students' reflections and in the classroom when you talk about this with the students and have the students talk to each other about it. In any case, I'll mention at this point that the longer project takes this discussion a little more leisurely. I actually have students consider the solution of another problem from Al-Khwarizmi's algebra to sort of get them into the process of dealing with rhetorical algebra, and more importantly, figuring out how the symbols they're asked to work with in an algebra course relate to a problem-solving situation. I have them work on a legacy problem from the algebra. In fact, here I can show that to you. This is the slightly longer version of the project. I'll scroll through. It has a slightly longer historical interpretation. Here's the legacy problem. I don't want to spend too much time here talking about it, but this is a problem that leads to what in modern algebra we would write as a linear equation. So it's a gentle introduction to solving algebra by these rhetorical means. Okay, I'm going to go back to the shorter project because there my focus is more directly on solving quadratic equations. In any case, the students are asked to look at what Al-Khwarizmi writes here, the sorts of things that we now consider as quadratic equations. In this task 3, I have them make the connection between what Al-Khwarizmi is saying in words and what we generally write down in symbols. And then I have them continue Al-Khwarizmi's presentation here, because he goes right away to presenting an example of such a problem. You'll notice that there are circled numbers in the text. I have introduced these into the text for the purpose later of making it easier for the students to refer back to the text. These numbers are not in the original. This task 4 is where I assist the students in trying to make sense of the text here and formulate this in modern symbols and to solve it using modern methods. But also to recognize that these modern methods are really essentially the same as what Al-Khwarizmi has instructed his readers to identify here, right? He suggests certain arithmetic steps that can be interpreted in the solution of the problem. This is complemented by a presentation of Al-Khwarizmi's demonstration of the method. Al-Khwarizmi realized that the problem solving could be connected to something more formally explained by means of a demonstration. This is more in line with Greek methods, right, where they're interested in demonstration. And here is one of the 2 demonstrations that Al-Khwarizmi presents for solving such problems. And in fact, he uses exactly the same example problem that the students would have just solved to provide the demonstration, where the unknown, or the thing, as he calls it, is represented by a square. Here, the portion of the diagram in the lower left. I'm sorry, the thing would be the side of the square, yes. And the grand square here is his method of solution that takes the given square, and in his case, and 10 roots. Well, those 10 roots would be multiples of the thing, the unknown. And they are identified as split up into these 2 rectangles that are appended to the side of the square of the unknown. These are equal to 39. So this collection of 3 pieces of the diagram amount to 39 objects. He uses dirham, the name for the currency, as a way of concretizing quantities, right? And so the idea is to complete the square by figuring out how large a square one needs in order to complete this figure. It's clear that when you split the 10 roots into 2, you have 5 roots here and 5 roots there. And so this dimension of the corner is 5 by 5 square. And so 25 is exactly what needs to be added to the square and the 10 roots to make up the larger square. The 39 plus the 25 is the 64 that represents the grand square, or what he calls the larger quadrate, right? And that shows in geometric form the method of the algebra. this is all worked out for the student or laid out for the student in steps here in task 5. So this task and the earlier one, task 4, I think, are the crucial heart of this project. And having students work through those 2 tasks are the important pieces here. The last 2 tasks, 6 and 7 here. 6 is asking the student to repeat this graphical analysis, this geometric analysis for a slightly different problem to make sure they understand what's going on. And task 7 sort of wraps things up by asking them to reflect on why Al-Khwarizmi needed to have the number of roots in order to produce the 2 rectangles that were appended to the square of the thing. In other words, why does completing the square do what it does? Yeah. I also asked them to think about why we call these quadratic equations, because in fact, the word quadrate is right there in the analysis, even though students rarely get any sort of geometric information along with solving quadratic equations in a typical algebra course. Finally, one more example for them to test out so that they understand how to complete the square. At the end, I have a couple of paragraphs that ask the students to reflect on the introduction of symbolism here. Symbols in algebra come much after Al-Khwarizmi himself. On the other hand, the symbols allow us to unite all of the various species of equations that Al-Khwarizmi had listed as different kinds of problems into one simple form. So, deriving the quadratic formula follows right from the completing the square method. And in fact, I point the students to a pair of appendices that follow this text here, where they can extend their discussion here. Appendix A asks them to derive the quadratic equation itself from the completing the square method through this task A. And in task B, we have another interesting bit of text from Al-Khwarizmi where he understands how it is that certain quadratic equations may not have solutions, right? He talks about problems of this type as being impossible, right? That's a very interesting choice of word, but of course it's perfectly reasonable for Al-Khwarizmi in the 9th century to be using this kind of language. So task B asks students to think about what it is that Al-Khwarizmi is talking about here and to connect this to the quadratic formula itself, in particular the discriminant of the quadratic equation, which I don't name here, but the students should be able to make a connection with. The project itself is followed, as are all of our projects, with extensive notes to the instructor to give implementers some indication of how to use this in class. I think that wraps up my walkthrough of the project. So I'll stop talking now, and I can take questions from anyone who's interested in asking questions.
Danny,
Yes, Dominic.
do you have any experience yet of using this in the classroom?
I have not yet used this in the classroom. I only just finished writing it over the summer, and I'm not currently teaching a course in which this would be appropriate. But I know people who are.
Yeah, so either of you know about their experience, or else you've certainly taught similar things in the past.
Well, I have taught similar things in the past. I've used this text from Al-Khwarizmi in my history of math course to show upper level math students where these algebra methods came from.
Is there a place that you would anticipate students would struggle while working through this?
Well, yes. The initial process of turning Al-Khwarizmi's words into symbols is something that very few students have tried on their own in the past. So that would be right here immediately. I don't think that advanced mathematics students would be terribly challenged by this. They may have questions. I think students early in their mathematical education, like those learning algebra for the first time, may in fact find this a lot easier than what they typically do in the standard algebra course because of the absence of the symbols. And I'm hoping that what gets done in the project is a way of assisting students to go from problem solving to symbolic manipulation through what it is that Al-Khwarizmi is doing here.
Yeah, that's interesting.
I also neglected to mention, while it's obviously suitable for algebra students to use, I can also see a strong argument for working this with elementary education majors, exactly the sorts of teachers who in late middle school will be introducing their students to algebra for the first time. Would anyone else like to pose a question?
Or share a related story or a relevant joke.
So Danny, how long do you think this takes?
Good question, Beverly. I think the mini project, the one that you see here that I talked through, it should take 2 days of classroom time plus some preliminary reading at the front end and time afterward to write up the tasks as formal homework. That's without the 2 appendices. If you add the appendices, that could take another day, possibly 2 more. All of this information, plus a little more, is found in the longer project, which differs from the shorter one only in the title, right? The longer one is called Solving Equations and Completing the Square. The longer one should take at least a week, maybe 4 50-minute periods would be my guess. Again, I haven't done this myself. Reza, have you implemented this in your classroom? No, not yet. I know that a couple of my, Phil, go ahead.
Oh no, I haven't implemented it, but I've been we actually are just taking a test at the end of this week, and then I'm gonna then we're gonna begin polynomial equations. You guys hear me?
Yes, I can hear you.
Okay, and I was just curious. So the one I've been planning on this is the one that has like a July 28th date. Is that the from the beginning of algebra? That's the shorter one, maybe without the appendix, or is that the longer one?
That's an earlier draft of the longer one. Yes.
Yeah, because in the notes you mentioned about 4 50-minute period. So that would be the longer one.
Yes, sir.
And the shorter one is not. I can get that from you. That'll be on the web. That's maybe not currently on the website, but will be quite soon.
Correct. I should ask me, and I'll send you a copy. Yeah.
Yep. Thank you.
Sure. So Beverly, did that answer your question?
Yes, it did. Thank you, Danny.
Mm-hmm.
Any other questions, comments, or discussion at this point?
Yes, can you hear me?
Yeah.
Danny, my name is Jerry Krantz. I work with Beverly Wood. So the way we teach math, especially in the lower level courses, it's more of like a muscle thing. We have students work problems infinitum until they understand the steps, or at least that's what we're trying to do. But here, you're taking an approach where you explain the development of the process and show that it's not, that you can explain it in English words and not mathematical symbols, which tends to frustrate some students who aren't that comfortable with mathematical symbols. Could you see us incorporating this type of process where we spend less time doing muscle memory work in math education and actually explaining how the process came about and why the process works the way it does?
That's a great question, Jerry. And I suppose the way I would respond would be to say the muscle memory process can be very effective, and it trains students to take algebraic formulations of quadratic equations and produce the appropriate solutions, but it's unclear what benefit the student has once he or she has mastered that. What I think I'm trying to do here by providing an explanation of the procedure is, you're right, I'm sort of setting aside the procedural methods in favor of something more rational, in the sense that it follows directly from formulations of problems and produces answers, based on things that the student can visualize, like the completing the square process. I think one has to be clear about what the goals are here. I doubt that students who complete this project are going to be able to do so and be provided with the ability to quickly solve a quadratic equation. But yes, I would say that it certainly would help them to understand how it is the procedure works. And it's likely to serve students better if, in fact, they do have to master these procedures, right? I guess I, like a number of my students, would respond by saying, what benefit is it to me to be able to quickly solve a quadratic equation? What's the goal here? And it's not clear that we do so in a standard algebra course, right?
Right.
I'm not claiming that this resolves that issue. I'm just saying that this doesn't, it may give some meaning more quickly to the process than typically happens in an algebra course.
Right. Right. All right. Well, thank you very much for your response.
Sure.
I think you can hear me now, right?
Yes. Hi, Reza.
Okay. Praise the Lord. Thank you. Is the longer version of this project also available?
An early version of the longer project is currently available at the website. If you want a more updated version, please contact me and I'll send one to you.
Will do.
Again, all of the updated versions should be soon available at the website. Just haven't put them up yet.
I just want to make a real quick comment. One thing I found interesting as working through this is just the multiplication of some of the mixed numbers. You know, it took me. I'm so used to working maybe with input, you know, with just a single improper fraction rather than a mixed number. So I found that kind of interesting. Some of the calculations when he's adding, doubling, you know, the fractions of money. I found that kind of interesting thinking about how he went through that process.
Yeah, that's
It's a little bit different from the way I would typically double and take a third of something.
that's right. If I remember correctly, that's in the context of solving this legacy problem.
Yeah, definitely in that one. And
task 2 here. Yeah, I think he doubles by adding it to itself rather than by specifically multiplying by 2. Yeah, this is the longer version, and here's the task in which a rhetorical problem is presented that leads to a linear equation, and it's a way of introducing the students to this process of turning, well, we would call it today a word problem, right? Turning a problem in which there is some unknown quantity, right? And reformulating that in terms of a modern algebra process, right? By building symbols to attach to the words. And again, I use these circled numbers to help the students negotiate their way through the text.
Well, we'd like to thank everybody for joining us today for this. Some of you I know are using projects or writing projects already. Thank you very much, and do take a look at what you want to sign up for spring, because we would love to hear from you.
Yeah, thanks everyone for participating. Thanks for the good questions. And, as with all of the webinars that we've run this fall, I think this is the 4th of the ones this fall, you'll find a recording of this posted at the Triumph's website soon enough.
Thank you, Danny.
Sure, thanks.